Hey guys, so welcome to tutorial 1 for control systems. In this tutorial we're going to be doing two Laplace transform solutions, as well as a little bit more of a practical understanding of how closed loop control systems works, kind of thing. So to begin with, here's problem 1. What we need to do is solve this function given these initial conditions using what we've learned about Laplace transforms. So step 1 is to take the Laplace of both sides. And what that looks like is you want to separate each term out individually. So and then when you take the individual Laplaces of each of these, it's going to look a little something like this. Okay, so the next step is going to be to simplify this entire term and isolate ys from that term. At the same time, if you're comfortable, you can insert all of your initial conditions. So we have one y at 0 there, one y prime at 0 there, and another y at 0 here. So I'll do that now. So we have ys, which we can factor out from this term, ys, which we can factor out from this term, and ys that we can factor out from this term. And keep in mind to distribute the 6 into this bracket. So we'll have s squared minus 6s plus 5. And then we'll have our initial conditions there, and there, which, so now what we can do is insert our initial conditions. So this term here becomes a 1, but because there's an s there, it's just negative s. This term becomes a negative 1, but because of the negative 6 distributed into the bracket, we have a positive 6. And then, where's the other one? This one here is a negative 3, but because of the negative sign there, we get a positive 3, and then all of that is still equal to 0. So now what we can do is we can rearrange, bring all of these terms to the other side of the equal sign. And then after that, we can isolate y of s, and we will have s minus 9 over s squared minus 6s plus 5. So now comes the more interesting bit. What we're going to be doing is, I guess, this was part 2. Part 3, what we're going to be doing now is using partial fractions as a means of solving it to eventually get to the inverse Laplace. So what we'll have is this term, more importantly the right side of the equal sign, and we are going to factor this into two components. So we'll have s minus 9 over s minus 1 times s minus 5. And what we'll do is we'll break this into its components, and we'll set arbitrary coefficients, a over s minus 1 plus b over s minus 5. And now what we want to do is we want to find the common denominator for both of these. So we'll factor in the common denominator. So that will be a over s minus 1 times s minus 5 over s minus 5 plus b over s minus 5 times s minus 1 over s minus 1. And what this is going to simplify to is a times s minus 5 plus b times s minus 1 all over s minus 5 times s minus 1. And now, so you will see that the denominators are the same on both. We have an s minus 5 factor and an s minus 1 factor, but the numerators are different. We have s minus 9 on this side, and we have all of this on the other. We can now equate those two numerators to one another in order to solve for our a and b terms. So we'll have s minus 9 is equal to, and at the same time I'm just going to distribute in those terms. So we have AS minus 5A plus BS minus B. Now, the next step is to separate this into two equations so that we can substitute and solve for our A and B terms. And what we can do is we can isolate the terms with S's in them, these three. So we'll have S is equal to AS plus BS. We can factor out the S's, so we'll have S is equal to S, A plus B. Cross these bad boys out. And we'll be left with 1 is equal to A plus B. So this is equation number 1. Number 2 is everything that does not have S terms in it, so that's going to be this, this, and this. We'll be left with -9 is equal to -5A minus B. So that's our equation 2. And what we can do now is we can isolate this in terms of B. So we'll have B is equal to 1 minus A. We can substitute that value B into this. So what we're left with is -9 is equal to -5A minus 1 plus A. So we'll bring that to the other side. What we're left with is -8 is equal to -4A, and therefore 2 is equal to A, or A is equal to 2. Plug that back into this, and what we're left with, this value of A into that value of A, and what we're left with is B is equal to -1. Okay, so now that we have all that information, we have our coefficients. We can proceed to step 4, and step 4 is going to be substituting these two coefficients into this version of our equation. So what we'll have is y of s is equal to a over s minus 1, where a is equal to 2. So 2 over s minus 1. And then in the next step, I'll show you how to simplify that. And then we will have plus -1 over s minus 5. So as I mentioned, we want to simplify this. So what we can do is we can pull the numerator out, just as a means to making the inverse Laplace a little bit easier. So we'll have now 2 times 1 over s minus 1 minus 1 times 1 over s minus 5, or you can just present that as the -1 over s minus 5, whichever is easier for you. And now what we're going to do is we're going to take the inverse Laplace of both sides. And because we factor out that coefficient, we can ignore it from the Laplace, the inverse Laplace transform. And now, so the Laplace transform that we need to use for this form is going to be like this. So this is the important Laplace transform. This is the form that we have with our coefficients factored out. So both this term and this term follow that form. And so it's as easy as taking the variables and plugging them in where they need to be. Our equation is now back in the time domain, denoted by y of t. And so we'll have 2 times e t minus 1 times e of 5t. And that's all. Hey all, so we're going to get started on problem 2 now, which is finding the solution of this equation with this initial condition using the Laplace transforms. It's very similar to the previous question, and yeah, so we'll jump right into it. So step 1 is going to be applying the Laplace to both sides, and again, you want to separate each term of your equations out and apply the Laplace to them individually. Now we apply the Laplace transform. And so that's going to look like this. So next what we're going to be doing is rearranging and collecting our like terms. So we'll collect everything in terms of ys. We can factor ys out. So we'll have ys. And we can also at the same time plug in our initial condition, which will turn this term into 1. So we get minus 1 is equal to 1 over s minus 1. Now we can rearrange, bring this 1 over to this side. And here we can find our common denominator to amalgamate this into one term. And you see the ones cancel, and you're left with s over s minus 1. So now what we want to do is, after simplifying this term, we're left with this. And what we want to do now is isolate y of s, and we'll be left with so now what we want to do is using partial fractions to simplify our terms. And so what that will look like is this. Again, we want to split this denominator out, so we'll have a over s minus 1 plus b over s minus 4. And now, using these two terms on the right side of the equal sign, we can find a common denominator. So what that will look like is a times s minus 4 plus b s minus 1 to b over s minus 1, s minus 4. And now, again, as we did in the previous example, we can set this numerator equal to this numerator, as these two fractions, these two ratios are the same. So what we have is s is equal to a s minus 4 plus b s minus 1. And again, we can create two separate equations. Oh, actually, we have to expand this first. So it'll be as minus 4a plus bs minus b. And we can separate this into two separate equations where we isolate all the terms with a's, or pardon me, with s's in them, and essentially factor the s's out. So we'll be left with 1 is equal to a plus b, same as last time, and then all the terms without s's in them, and we'll be left with 0 is equal to negative 4 minus b. So now we have equation 1 and equation 2. We can do substitution again. What I'm going to do is put this in terms of b again. So we have b is equal to 1 minus a. And then over here I'll do my substitution. So we'll be left with 0 is equal to negative 4a minus b, which would be negative 1 plus a. And then what that gives us is we can bring the 1 to the other side. So we have 1 is equal to negative 3a, and a is equal to negative 1/3. Pop that back into this equation, where we get b is equal to 1 minus negative 1/3, and we get 4/3. So now with our two coefficients, what we can do is we can take these numbers and put them back into this version of the equation. I'll do that over here. So we have y of s is equal to, and you can factor out this coefficient just to make everything look a little bit cleaner. So we get negative 1/3 times 1 over s minus 1 plus 4/3 of 1 over s minus 4. And then what we can do is take the negative, or the inverse Laplace of all terms in order to bring ourselves back into the time domain and find our solution. And just for notation, I'm going to include all the Laplace symbols. And then you can factor out these coefficients from the Laplace transform to further simplify our calculations. And then using the equations that we used for the previous example. And so to solve this, we use the same equation that we used for the last example, for the last problem. And what we end up with is y of t is equal to negative 1/3 e to the t plus 4/3 e to the 4t. And that's our final answer. Hey guys, so this next question, question 3, is a bit more of a theoretical modeling question, so there's no math directly involved. Essentially, the idea is that we have a satellite and we want it to track a star out in space. And the only angle that we're worried about is this rotation here, the rotation perpendicular to the surface of the ground. In textbooks, it's sometimes referred to as the azimuth angle. And so what we want to do is we want to present the closed loop control system that would be necessary for something like this to operate correctly. So the first thing that we would have would be our input, right? Our angular input. And so this would be the present input of the satellite. And then that would go into what is called the input block. And in this block would be our desired angle. So thereafter, we would have something referred to as a controller. And the controller is measuring the output of this summing block, and we'll get back to the summing block and why it's important in a few minutes. But essentially, if the desired angle is different from the measured angle, then there will be a delta between the two, and a signal will be created in order to fix or adjust that angle. So if the actual angle was different from the desired angle, a signal would be created inside this controller block. So that signal in the form of a voltage would be sent out of the controller and into the plant. And the plant is, in control systems, the part of the control system that is typically being like mechanically acted on. So in this case, it would be a large motor. And this is the motor that would actually turn the satellite about that axis. And then outside of that, we would have our output angle. Now, as mentioned previously in lectures, we can have a feedback loop which carries information with it. And so this output angle is then measured by a sensor. And in the case of our system, this sensor may take the shape of a potentiometer or any other kind of electromechanical transducer that measures angles. And then that angle would be fed into this summing block, and that would be what is used for the basis of determining the signal. And so this whole control system works together to essentially bring our satellite and its angle to the desired angle. If the present angle, if the output angle is significantly different from the desired angle or the input angle, there'll be a large delta in this summing block, and that means that a larger voltage, depending on the gain, is going to be sent to the controller, and therefore a larger signal will be sent from the controller to the motor, which means that the motor will spin faster to get to that desired angle. Yeah, so that's how you can model a control system without using math, just using these control blocks as a more abstract means of breaking the problem down. So yeah, thanks guys.